Another solution concentration is molarity. This is that mysterious capital M that we saw in chapter 15 and that has been showing up on reagent bottles all semester in the lab. Now we're finally at the end here going to learn what it means. Molarity is abbreviated capital M, and it's defined as the number of moles of solute per liter of solution. So moles of solute divided by liters of solution. This is more useful to chemists because, as you've noticed, we do a lot of calculations with moles, right? All the stoichiometry stuff had moles and moles in the middle of it. So chemists like to use molarity because it relates to number of particles. Notice that it's moles of solute per liter of solution, not liter of solvent, okay? I will not try to trick you with this one because it's actually just way too hard. It's not worth the trouble. But this is liters of solution. We're going to see another one that's actually kilograms of solvent, and that's one you have to watch out for. If we want to make a solution of a specific concentration in molarity, what we usually do is we put the solute in a flask and then we add water until the solution has the specified volume. You don't say, well, if I want a liter of this solution, I'm going to put in this much solid and I'm going to add a liter of water. That's not going to work. Think about it. If you have a drinking glass full to the top of water and you put a tablespoon of sugar in it, what's going to happen? It's going to overflow because the solid takes up some space. So we always look at the volume of the whole solution for this calculation. Here we have an illustration showing how you would make a 1 molar NaCl solution. So you would take 1 mole of sodium chloride. Of course, you can't weigh out a mole because the balance doesn't read in moles, it reads in grams. So you have to use the molar mass and figure out the mass. So you weigh out 58.44 grams of your solute and you put it into a flask. And then you're going to add water and dissolve this, and then you keep adding water until the meniscus gets to the mark on the neck of the flask. This is called a volumetric flask, and it's designed to hold one particular volume. This is a 1 liter flask. It's got a mark on the neck, and if you fill it up to there, you've got 1 liter of solution. And then you put a stopper on the top and you mix it. It's tricky mixing it at the end because if you just shake it, nothing's going to happen. You have to actually put a stopper on here and turn the whole thing over multiple times. That's making a solution. Let's calculate the molarity of a solution made by putting 55.8 grams of sodium nitrate into a beaker and diluting to a volume of 2.5 liters. So we've got 55.8 grams of sodium nitrate, and we've got 2.50 liters. And what are they asking us for? Molarity, right? Calculate the molarity. Well, molarity is moles of solute. What's our solute here? It's the sodium nitrate per liter of solution. Did they give us either of those quantities? Yes. 2.5 liters. That's the volume of the solution, diluting to 2.5 liters. They didn't say they added 2.5 liters of water. They said they diluted it, they added water until the volume was 2.5 liters. So we know the denominator, 2.50 liters. They didn't give us moles of sodium nitrate, they gave us grams. How can we find the moles? We need the molar mass, right? So we go to our handy dandy periodic table. Sodium is 22.99. There's one of those. And nitrogen is 14.01. There's one of those. And there's 3 oxygens. And we add those together. And I'm getting 85. That's what my calculator says, 85. Should that just have 2 significant figures? That's what my calculator shows me. We really should, if we're keeping track of significant figures, we should put 2 zeros there. Because these guys all had 4 sig figs. There's my pointer. These had 4 sig figs. And kind of the cheater rule for molar mass is if you're using 4 sig figs in all your masses for your elements, then use 4 sig figs in the mass for your compound. The more thorough way is we look, these all have 2 decimal places. Our answer should have 2 decimal places. Either way, we need that. So the units on that are grams per mole. 1 mole weighs 85 grams. So we can go back up here to our mass, and we can convert this by multiplying by moles and dividing by grams. So 85.00 grams is equal to 1 mole. 55.8 divided by 85. 0.656. That has 3 sig figs. But I'm going to carry 2 extras so that I don't have rounding errors. That's my moles. I take the moles of solute and I put it into the equation for the molarity. Oops, I almost wrote grams. That's not grams, it's moles. So 0.65647 divided by 2.50, and I get 0.263. The units there are moles per liter, right? That's what we've got here, moles per liter. Another way to represent that is with the capital M, 0.263 capital M. I underline my capital M's because when you're using handwriting, is that a capital M or a lowercase m? Whatever you answer, I can make it wrong. You say, oh, well, that looks like a lowercase m. No, that's a capital M. So if you underline your M, that indicates that it's a capital. Oops, didn't mean to do that. Any questions? We used mass percent as a conversion factor. We can also use molarity as a conversion factor. It's useful as a conversion factor between moles of solute and liters of solution. So let's do an example. How many grams of sucrose are contained in 1.95 liters of 0.781 capital M solution, sucrose solution? When you read this, you read the capital M as molar. Same word as the teeth in the back of your mouth. 0.781 molar. I encourage you, when you write this down on your paper, don't write the capital M. Write moles per liter. Because otherwise you're probably going to forget that it means moles per liter, and you're going to be at a loss because you don't see liters anywhere. And you won't recognize that it's a conversion factor. Did not mean to do that. So what we've got here is we have 1.95 liters. We have 0.781 moles per liter. And we want to know how many grams of sucrose are in there. These concentration problems a lot of times come down to unit conversions. I have to start with one of these, and I'm trying to get to grams of sucrose. This one looks like a conversion factor, so I don't want to start with that one. I want to start with this one. So I'm going to start with liters of solution, and I'm going to try to get to grams of sucrose. 1.95 liters. Do I know a relationship between liters and grams? I don't see one in here. Liters and moles? This would allow me to convert from liters to moles. So I could get to moles. Could I go from moles to grams? Oh yeah, we've done that lots of times. So this stupid stylus. This is a fancy schmancy one, and sometimes it works really great. My cheapy one that I stole from the after-school program works great, but I lost it, so I'm going to have to steal another one. 1.95 liters. Liters to moles. So my next one here is going to be moles and then grams. And then I'm going to put the units in so they'll cancel out moles, cancel out liters. The molarity is a conversion factor between moles and liters. So 0.781 moles, I'm going to put the 0.781 with the moles. And then grams to moles, that's a molar mass. We were given the formula for sucrose. I think it's 342. 12 times 12.01 plus 22 times 1.008 plus 11 times 16, 342. 342.3. So now we just do the multiplication, and actually there's no division in this one. 1.95 times 0.781 times 342.3. And this gives us, with 3 sig figs, 521 grams of sucrose. Is that possible? 1.95 liters, so that's almost 2 liters, right? It's a lot of sugar, 500 grams of sugar, but it's a pretty big volume, and sugar's pretty soluble, so yeah, that's probably reasonable. If you had 5 million, maybe not. Usually if the amount of the solute is more than the amount of the whole solution, you've got a problem. Any questions? I think we have another example. How much of a 0.225 molar KCl solution contains 55.8 grams of KCl? Well, let's write down our numbers. 0.225, capital M. I'm not going to write capital M. I'm going to write moles per liter, because that reinforces to my brain this might be a conversion factor. And then I've got this number, 55.8 0.8 grams of KCl. What are they asking us? How much solution? I don't like how this question is worded. How much solution? Well, do they mean mass? Do they mean volume? It doesn't say. What would be the easiest? Liters would be the easiest, right? Because here we've got the relationship between moles and liters. So if we find how much, and think of it, a solution is a liquid, this solution is a liquid, and so a volume would be pretty easy to measure. So we're going to look for liters of solution. I would prefer this to say how, I hate you, stylus, how many liters of this solution? That's a better question. So we're trying to find liters. Here's liters over here. Which of these numbers are we going to start with? The grams. It's got just a single unit, could not be used as a conversion factor. So let's try starting with that. 55.8 grams of KCl. And then we're trying to bridge this gap and get over to liters. Sometimes it's easiest to work backwards. Liters, well, I've got this guy. I should probably try to use him, right? Relates moles and liters. So I could convert moles to liters using the molarity. And then I've got grams to moles, and that should be like an old friend by now. That's the molar mass. So 55.8 grams of KCl. And we're going to go to moles. And then we're going to go to liters. I'm going to put the units in here so they cancel out. And here at the end, liters and moles, that's this here. 0.225 is with moles, and so I need to put it down here in the bottom with moles. That would be 1 on the top. Molarity, no, that's not molarity. Molar mass would be 39.10 plus 35.45 potassium plus chloride. I'm getting 74.55. So 74.55 grams down here, 1 mole up there. 55.8 divided by 74.55 divided by 0.225. Again with the 3 sig figs. 3 sig figs, 3.33 liters. Any questions? So when we report the concentration of a molecular solute, that dissolves into molecules, and the molarity indicates the number of moles of molecules dissolved in the solution. But for ionic solutes, when we're reporting a concentration, we're actually reporting the concentration of the solute before it's dissolved in solution. So a 1 molar calcium chloride solution has 1 mole per liter of calcium chloride formula units dissolved in it. But when this dissolves, it actually forms 1 mole of calcium ions and 2 moles of chloride ions per liter. Usually we don't really talk about the concentration of the ions, we just talk about the concentration of the compound as a whole. But the concentration of those individual ions can be approximated from the overall concentration. So determine the molar concentrations of calcium and chloride in a 0.75 molar calcium chloride solution. And we're going to do this just looking at the chemical formula. Calcium chloride. When that comes apart into ions, we get calcium ions and we get chloride ions. How many of each? If we have one of these, how many calcium ions do we get? 1. And how many chloride ions? 2, because this has 1 calcium and 2 chlorides. So if we have 0.75 moles per liter calcium chloride, how many moles per liter of calcium ions are we going to have? Well, how many moles of calcium ions per mole of calcium chloride? What's the mole ratio? 1 to 1. So the concentration of the calcium ion is the same. But when we do this with the chloride ions, it's a little different. Moles of chloride per mole calcium chloride. What's the ratio here? 2 to 1. There are 2 moles of chloride for each 1 mole. 2 moles of this for every 1 mole of that. So I'm going to end up with 1.50 moles per liter of chloride ions. Any questions? Because ionic compounds come apart into their individual ions.